Hello friends, welcome to my YouTube channel. After quite some time, I am back again with some purely mathematical contents. Title of my today's video is the characteristic polynomial and the minimal polynomial of a square matrix have the same irreducible factors. So this is a linear algebra stuff. In this video, using an elementary method, we show that the characteristic polynomial and the minimal polynomial of a square matrix have the same irreducible factors. So we need some preliminaries. So let F be a field and A be an n cross n matrix over the field F, where n is a natural number. Let In denote the n cross n identity matrix. Let X be an indeterminate. What is characteristic polynomial of a matrix? The formal expansion of the determinant, this one, this is Xin, that means a diagonal matrix whose diagonal entries are X, and minus the matrix A, and then consider the determinant. So expand it formally in the form of a polynomial in the ring Fx. Then that particular polynomial is called the characteristic polynomial of A over F. An important result concerning characteristic polynomial is this one. It's called Cayley-Hamilton theorem. Every square matrix satisfies its own characteristic polynomial. In other words, if Qx denotes the characteristic polynomial of a matrix A over F, then Qa is the n cross n zero matrix. So Cayley-Hamilton theorem says that there exists a polynomial, a non-zero polynomial or a polynomial of positive degree which is satisfied by A. And minimal polynomial is the polynomial mx of least positive degree in Fx such that Ma is the n cross n zero matrix. So Cayley-Hamilton theorem confirms the existence of such an Mx. Now, using the division algorithm in Fx along with the Cayley-Hamilton theorem and the minimality of Mx, one can easily see that the minimal polynomial of a square matrix is a factor of the characteristic polynomial of the matrix. In other words, minimal polynomial of a square matrix divides the characteristic polynomial of the matrix in Fx. In particular, every irreducible factor of the minimal polynomial of a square matrix is also a factor of the characteristic polynomial of the matrix. In this video, we show that the converse is also true. In other words, every irreducible factor of the characteristic polynomial of a square matrix is also a factor of the minimal polynomial of the matrix. So let us start. Let Mx be the minimal polynomial of A in Fx. Let Y be another indeterminate. X is an indeterminate, we have chosen Y to be another indeterminate. And then you consider the polynomial mx minus my, which is a polynomial in two indeterminates. So it is an element of the ring fx comma y, polynomial ring in two indeterminates. So if x is equal to y, this side will be, this will be 0, 0 polynomial. Clearly, x minus y is a factor of mx minus my in fxy. Okay. Thus, mx minus my can be written as a multiple of x minus y, that is x minus y into some fxy, where fxy is a polynomial in two indeterminates x and y. So it's an element of fxy. Now putting xin in place of x and putting a in place of y, we get the following matrix equation. So if we replace this x by xin and this y by capital A, then what we get? We get this mxin minus ma is equal to, earlier it was x minus y, so it is xin minus a, and then this is fxin comma capital A. Or since mx or my is the minimal polynomial of a, and therefore a satisfies this my, so that means ma is 0 matrix. Therefore, this line can be written as mxin equal to xin minus a fxin comma a. Okay. Now considering the determinants of both sides, we have, so if we consider the determinant of both sides here, we get determinant of mxin equal to determinant of xin minus a into determinant of fxin comma a. Now what is this? Note that mxin is actually equal to mx into in. That means a diagonal matrix whose diagonal entries are mx. So it is mx, mx, mx down the diagonal. And so determinant of this will be equal to determinant of this, which is mx to the power n. N is the size of this identity matrix. Now how this is possible? An explanation is given here. Suppose we write mx is equal to this polynomial a0 plus a1x, a2x square plus and so on, akx to the power k. Then mxin, that means if you replace this x by xin, so it will be x will be replaced by xin. So a0 will become ain, there is no x here. a1x will become xin, a2x square will become xin whole thing square, and this x to the power k means xin to the power k. Now these two are all right, but xin square means xin into xin, two diagonal matrices, when we multiply, the corresponding diagonal elements get multiplied. So it is x square in. Similarly, this is x to the power k in. So take in on one common. So what remains is a0 plus a1x plus a2x square plus akx to the power k into in, and that's, this part is mx only. So what you get is mxin is equal to mx into in. So that explains the equality of this. Now if we expand this determinant equation formally, if we expand these determinants formally as polynomials in x, Then this part gives the characteristic polynomial of A. This part gives the mx to the power n. That means characteristic polynomial of A divides mx to the power n. This will be just a polynomial in x. So what we get here? Hence, considering the formal expansion of the determinants in the above determinant equation in the form of polynomials in fx, we see that the characteristic polynomial of A is a factor of the polynomial mx to the power n in fx. So, in particular, every irreducible factor of the characteristic polynomial of A is also a factor of the polynomial mx to the power n. But since we are starting with an irreducible factor, so if an irreducible polynomial divides this power, that irreducible polynomial will divide mx also. Thus, it follows that every irreducible factor of the characteristic polynomial of a square matrix is also a factor of the minimal polynomial of the matrix. Hence, our goal is achieved. So, thanks for watching. Hope you have enjoyed the video and it will be useful for you. Thanks.